Imagine a new kind of artificial intelligence. Not just smarter, but smarter the way our brains are. That's exactly what the Hierarchical Reasoning Model, or HRM, brings to the table. And today, we're diving deep into this revolutionary paper, page by page, idea by idea, to uncover how HRM is redefining what AI can do. Let's start at the beginning. The reasoning challenges in AI. Right now, large language models, the giants like GPT and Claude, have a big limitation. They're like sprinters, fast, but they can't run a marathon. Why? Because their reasoning depth is fixed. They can't handle problems that need long, complex chains of thought, especially ones that require polynomial time or algorithmic precision. They're not Turing complete. They can't think like a computer program. In chain of thought prompting, it's clever but fragile. One wrong step in the chain and the whole reasoning collapses. Plus, it needs tons of training data and generates tokens slowly, making it inefficient and brittle. So the question becomes, can we build an AI that reasons deeper, faster, and more efficiently without needing millions of examples? Enter HRM, a brain-inspired approach to complex reasoning. This isn't just another neural network tweak. It's a fundamental redesign, inspired by how the human brain processes information. The brain doesn't think in flat, linear steps. It uses hierarchy, rhythms, and feedback loops. Different brain regions handle different levels of abstraction, from raw sensory input to high-level planning, and crucially, they operate on different timescales. The HRM mimics this with a stunningly elegant two-module architecture. Meet the high-level module, the slow, strategic thinker. It's like the CEO of the system, making abstract decisions, setting goals, and updating only once every cycle. Then there's the low-level module, the fast, detail-oriented worker. It crunches the numbers, runs the computations, and updates at every single time step. Here's the magic. They work together. The input comes in, gets encoded, and then the low-level module goes to work, using the current state of the high-level module to guide its fast, detailed processing. After a set number of steps, say T time steps, the low-level module finishes its cycle. Then, and only then, does the high-level module update using the final state from below. And this repeats for n full cycles, building deeper and deeper reasoning, step by intelligent step. Mathematically, it's clean and powerful. The input is transformed once, the low-level states evolve over time, the high-level states update only periodically, and the output? It's generated from the final high-level state after n cycles. The total computation? N times t steps, but with a structure that enables true depth. Now here's where HRM gets really clever. First, hierarchical convergence. Instead of letting the whole network drift or converge too early, a problem in traditional RNNs, HRM lets the low-level module reach a local equilibrium within each cycle. This means it stabilizes its thinking before passing the baton up. The result? The system maintains high computational activity over many steps, achieving an effective depth of NT without instability. Second, approximate gradient. Training deep recurrent models usually requires backpropagation through time, BPTT, which is memory-heavy and biologically unrealistic. HRM ditches it. Instead, it uses a one-step gradient approximation, inspired by deep equilibrium models and the implicit function theorem. This slashes memory use from O of t to just O of 1 and makes learning way more efficient. And yes, it's also more like how brains might learn. Third, supervision. To keep training stable, HRM gives the high-level module frequent feedback. It detaches the hidden state between cycles, creating a one-step approximation of the recursive process. This acts like periodic check-ins, ensuring the model stays on track, just like neural oscillations in the brain that synchronize activity across regions. And here's the kicker: adaptive computational time. HRM doesn't just think, it learns when to stop thinking. Using a Q-learning algorithm, it decides dynamically whether to continue or halt. This means it can think fast for easy problems and think slow for hard problems, just like Daniel Kahneman's famous idea. And at inference time, it scales computation based on complexity: smarter, faster, leaner. Now let's talk results, because HRM isn't just theory, it crushes benchmarks. On the ARC-AGI challenge, a tough test of abstract reasoning, HRM hits 40.3% accuracy with just 1,000 training samples and only 27 million parameters. No pre-training, no massive data, just pure reasoning power. Compare that to chain-of-thought models, which fail completely on the same tasks. It solves Sudoku Extreme with 74.5% accuracy, again, with minimal data. And it navigates 30 by 30 mazes, which are a nightmare for most AIs, with 55% success rate. Meanwhile, COT models, they score 0. 0. HRM isn't just better, it's doing what others can't. And get this: HRM beats massive models like Claude 3 and DeepSeek R1 despite being tiny in comparison. 27 million versus billions. It's like a go-kart outracing a freight train. Why? Because HRM isn't just efficient, it's organized. And that organization, it mirrors the brain. In mouse cortex studies, scientists found a clear hierarchy. Higher brain areas have higher dimensionality, more diverse, flexible representations. The participation ratio, a measure of neural diversity, increases from sensory to associative regions. The correlation, a strong 0.79, and the PR ratio between high and low areas is about 2.25. Now look at HRM. After training, its high-level module has a PR of 89.95, the low-level just 30.22, a ratio of nearly 3. That's not a coincidence. That's emergent brain-like structure. And here's the most exciting part. This hierarchy doesn't exist at the start. In untrained models, the modules are flat, no separation. But after training, a clear, functional hierarchy emerges. The high-level space expands with task diversity. The low-level stays focused. This is self-organized intelligence, just like in biology. Why does this matter? Because high-dimensional representations are key to cognitive flexibility. They prevent neural collapse. They enable complex reasoning. And they mirror the prefrontal cortex, the brain's command center. So what's the big picture? HRM achieves near-perfect accuracy on hard reasoning tasks with tiny data, tiny model size, and no pre-training. It overcomes the depth limits of transformers. It eliminates the need for chain-of-thought prompting. It reasons in the latent space without relying on language. And it does it all with a structure that's not just effective, but biologically inspired. This isn't just an AI model. It's a new paradigm. And the future? Just getting started. The team wants to explore the causal mechanisms behind this hierarchy, design smarter gating systems, apply HRM to scientific discovery, and push it toward universal computation, a general-purpose reasoning engine. In their words, HRM represents a promising direction toward next-generation AI reasoning systems with universal computational capabilities. So if you're excited about AI that doesn't just talk, but thinks deeply, efficiently, and like a brain, then HRM isn't just a step forward, it's a leap.